So today we have our very own Alessio, who will be talking to us about angular correlations in rare B decays at CMS. So Alessio did his master thesis in Padova in 2014, looking for the semi-leptonic B decays in TT bar events at the LHC. He then did his PhD on angular parameters in the decays of B zeros. Also at the LHC, and he's been at LIB in the CMS group since 2020. He's had many coordination roles in the B physics group at CMS, including convenership of the trigger group, the property and production group, and rare decay groups. And he's also served as the data analysis coordinator. So currently he also coordinates the commissioning of the barrel timing layer detector. So please take it away, Alessio.
Thank you very much for the presentation. And thanks everybody for being here and hear me talk about this new analysis that we released and that the LIB group, LIB CMS group, had involvement in. So it's a very good forum, I think, to talk about this analysis. So these are the outlines of the talk. So I will start with an introduction on the B to SLL transition. I will then go more in depth about the analysis, the angular analysis of one particular example of this transition, so the B0 to K star 0 mu decay. And then I will present the new measurement performed by the CMS Collaboration. And I will end with the future prospects of this kind of analysis. So, standard model, we know it's a very successful model so far. It managed to, let's say, survive a lot of scrutiny, a lot of measurements, a lot of tests. At the moment, direct searches are not showing us any clear path to new physics. So we have to let's say, rely on indirect searches in order to start to find hints, evidences for where to look. And one very good environment where we can do this kind of indirect searches is the B2SLL transitions. So these transitions are rare decays. These transitions are rare decays, and as such, they are quite sensitive to the virtual contribution of new particles that may have lower coupling low couplings with the standard model particles or very high masses, and so we need to let's say, increase this sensitivity. So these are flavor changing neutral currents, and as such, in the standard model, they cannot happen at tree level. So the leading order diagrams are the one described here, the penguin diagram and the box diagram, which are the main contributor for the standard model decay. However, beyond the standard model can contribute in two ways. Can enter in these diagrams with, for example, a charge X instead of the W, or in other ways. Or can also mediate these decays at tree level, so with, for example, a new gauge boson or a leptoquark can enter at tree level, and so let's say we have a quite good sensitivity over these kind of scenarios. In order to describe in a model-independent fashion this kind of decay, so not to be constrained by the, let's say, assuming standard model decay, what we use is the effective field theory. So basically, we allow additional terms in the Lagrangian up to the 6-dimensional terms, and basically everything that is higher, much higher, at a much higher mass scale than the B-hadron masses, we can compact it in a single point interaction. So all these kind of decays that can involve standard model particles or new physics particles can be described by a single interaction point. So you can see how then these 6-dimensional terms of the Lagrangian would look like. And here, in this way, we can factorize 2 components. The Wilson coefficients, C, that describe the short distance contribution, and we can have a good calculation, can compute in the standard model case with good accuracy. And these are where high mass new physics would enter. So we are looking for discrepancies between standard model values and the measured values in these Wilson coefficients. And on the other side, this operator, O, that encoded the long distance contributions, and we will see later that can be affected by uncertainties on the hadronic form factors. So here, just to clarify a bit, which are the Wilson coefficients that we are probing with this type of decays. Here you can see a list of, these are 5 plus the primed versions, so 10 in total, C Wilson coefficients. Here they are operators, so they encode different kind of currents. And you can see that how different type of transitions, so the radiative transition, the B2SLL transition, the one we will talk about, or the BS decay into muons, you see that these transitions are sensitive to different set of Wilson coefficients. Using these Wilson coefficients and the operators that presented earlier, we can then describe this B2. Here we build then the transversity amplitudes for the hadronized version. So far I always talk about the B2SLL transition. So it's a quark level transition, but we know that quarks don't live on their own in real life. So we always have spectator quarks that don't take part in the hard interaction in this transition. So they don't take part of this vertex, but are there, are spectator quarks. So we can then write our decays as a generic B2 meson lepton decay. And here you can see how we can express this, the transversity amplitudes of this decay as a function of the Wilson coefficients and of a set of form factors that can be distinguished between local form factors that describe the gluon exchange between spectator quark and the several quarks involved in the transition, so QCD interactions, and the non-local form factors that are a bit more tricky to calculate. We will see later that exist different models to calculate this, to interpret these non-local form factors. And in general involve one of the most, let's say, important contribution to these non-local form factors is the charm loop transition that with virtual charm loop happening that produce the 2 leptons. Okay, so one very important quantity that we need to include in our analysis in order to have a better understanding of this decay, a better analysis of this decay, is the dimuonic baryon mass. So as until now I mentioned that we have these 2 muons that are produced, you can see there is no resonance producing them, and they can populate a spectrum that depends on the phase space of the decay, and the phase space available for the decay, and analyzing the spectrum of the 2 muonic baryon mass allow us both to isolate the contamination of the transition, the decays that involve charmonium resonances. So we know that we have this the 3 levels, so much more enhanced according to the standard model, decays where the B decay in C bar, and NS quark. And when the CC bar produces a charmonium resonance, this can decay into muons and so produce exactly the same final state as our the transition that we are interested in. So this is an irreducible background. So the only way we have to isolate it is indeed to split the dimuon invariant mass spectrum and dedicate some regions to contain this particular decays that will peak in this spectrum. Then you can see here that we have regions where the rare mode, so the non-resonant mode, is dominant, and the dependence of the influence on this rare mode of each Wilson coefficient will depend also on the region of Q square. So you can see that at low Q square, the C7, C9 are the one most dominant and dominate the decay, while at high Q square, this is dominated by C9 and C10, and their prime version. So effectively what we will do in our analysis, what has been done, is to perform them by splitting the Q square range in bins and perform independent analysis in these bins of the spectrum. And two of these bins will be dedicated to the J-psi and psi2s resonant modes that are usually employed as control channels for the analysis because of the large statistics. So they're very good control channel. Okay, so what can we do with this kind of, which observable can we measure? The first one coming to mind is the measurement of the branching fraction of these decays. So these are relatively, it's never a very easy analysis, but compared to the other type of analysis, it's easier from the experimental point of view. However, the standard model predictions for this branching fraction are quite subject to uncertainties due to the form factors. So you can see here an example from quite recent CMS analysis where the branching ratio of the B plus to K plus mu has been measured, the differential one as a function of Q square. And you can see that here we have several models for the predictions, and some of them are present very large uncertainties. So they use different ways of computing non-local form factors, and each of them is subject to different uncertainties, but in general, this comparison between experiments and data, it's almost always dominated by the uncertainties on these non-local form factors. What can we do then? We can also do a lepton flavor universality test, so comparing the decay going in a family of leptons with the decay going to another family. So muons usually are the one experimentally easier to work with, and indeed when we do branching fraction measurements, we mostly use muons, especially at hadron colliders. The angular analysis I will present later is also using muons, but we can also do the comparison, the ratio between the branching ratio of the muon decay compared to the electron decay. So this is what we call R, and the benefit is that in this ratio, all the uncertainties coming from the form factors are simplifying, and so the theory prediction is very clean. This is more challenging to perform experimentally because indeed we have to work with electrons that are a bit more tricky, but okay. But let's say it's still very interesting. And you can see here the most recent measurements from LCP and the last one from CMS that show that there is a good consistency with a ratio of 1, that is what the standard model predicts. So let's come to the analysis of the day. So the angular analysis of this particular decay, the B0 to K star 0 mu. So what's an angular analysis? An angular analysis basically uses the angles between the final state particles of the involved in the decay and analyze basically their distribution. So this particular decay, where the K star decay in a in a pair, a kaon and a pion, can be fully described by the dynamic invariant masses I mentioned earlier, and the three LHC angles, theta k, theta L, and phi. You can see here their definitions, so basically are the decay angles of the hadronic system, theta k, leptonic system, theta L, and phi is the angle between the two decay planes of the two systems. And basically, okay, so we can then express the decay rate of our decay as a function of these three angles using this sum, this polynomial of spherical harmonics. So you can see here, this is a bit complicated, but we can go through. Let's say each term of this polynomial has a dependence on this angle to the spherical harmonics, and then we have a set of coefficients that parameterize this polynomial. So the only one with clear physical meaning is FL, that is the fraction of K star of events with a K star that is produced with a longitudinal polarization. The other are quite arbitrary coefficients of these terms. You can just notice that they are not just simple coefficients. We don't have a parameter in front of each term, but we have also the square root of sometime 1 minus FL times FL, or other terms that depends on FL. And this is done to optimize this basis of parameter and basically absorb, at leading order at least, absorb all the dependency on the form factors in this term here. So basically our P parameters have the benefit that at leading order they are not dependent on the form factors and their uncertainties. So, so this is quite clever way of having, let's say, what we cannot do with the branching ratio, where we have a single parameter, so it's fully dependent on these uncertainties. Here, since we have a set of 8 parameters, we can just include in a single one of them all the dependency on the uncertainties, and then have the other 7 more clean. So the goal of an angular analysis is then to determine this set of coefficients and their dependence on Q square. So what were the previous results before this analysis? So this angular analysis of this particular decay was performed several times by different experiments at LHC, Tevatron and B-factories. You can see here some of the latest results. This is you can combine the one below. It's an update to the LHCb. This is the top one, include the LHC experiments, CMS and LHCb up to run 1. This is an update, including LHCb with the 2016 data. And the most striking things that we can notice is that the LHCb measurement observes some tensions in one of these angular parameters, phi prime. That is the one that I'm representing here. Where you can see in the low Q square region, low dynamic invariant mass region, we have a p phi prime value that is visibly higher than the predictions. So with this new analysis, this is also increasing the interest that we have in this particular decay. So we will see. We'll discuss later a bit more about this comparison of the results. Just let me mention that thanks to this effective field theory, we can basically translate all these measurements in values for the Wilson coefficients, and then combine them in global fits with other measurements. So B2SLL branching fraction, for example, or the BS2mu measurement. So you can see here, for example, a 2D plot, a 2D fit with C10 and C9. These are new physics components, so the standard model is at 0, is shifted to be at 0. And you can see all these contour plots are different type of analysis. And and the angular analysis, well, the global fit is the blue one, the small one here. And this, let's say, translating this tension here, that we see in P5 prime, in a tension on the C9 Wilson coefficient. And you can see that in general, it's also good to see that all these analyses, all these results have a good agreement with each other. So it's let's say the chi-square of this global fit is quite good because so it's every let's say even if not all of them are in tension with the standard model, at least they are all agree with each other in pointing toward a shift in C9. Okay, so let's come to this analysis, new analysis CMS. So let me first present a bit the CMS detector. Well, we had a seminar on CMS end of November, so you should remember quite well. But let's say this is a general purpose detector, so it's a classic layer detector that has the silicon tracker in the center. The two calorimeters, the electromagnetic and hadron calorimeters surrounding it, and then the muon chambers all around. I won't go through the detail of all the detectors, but let me just mention the two detector systems that we use in this analysis. So the silicon tracker that is able to have a good efficiency already from 300 MeV tracks, hadronic tracks with the transverse momentum of 300 MeV, and a very good resolution of the position of the reconstruction of the vertices between tracks. So you can see here the tracking efficiency for offline reconstructed tracks, and you can see that we can really go to very low PT. That in B physics decays is a really important quality. Secondly, we make, let's say, we use also the muon chambers to identify the muons in our decay. This can go up down to a PT of 3.5 GeV in the barrel region, in the central region, and 1.5 GeV in the forward region. You can see here the efficiency curves, and you can see that also this is extremely important for the physics applications. And we have an excellent resolution on the momentum, and so that translates in an excellent resolution on the muon mass. So you can see an example for the Upsilon system of the resolution that we managed to achieve the order of less than 100 MeV. So these are all critical qualities in order to have let's say a good analysis, a good measurement for our decay. So CMS collected a lot of data in the past, in the full lifetime. Just a reminder that the LHC runs collected so far are divided in 3 major runs. So run 1 collected up until 2012. Run 2 from 2015 to 2018, and run 3 that is currently ongoing and started in 2022. This analysis will use the data of run 2, except 2015 because it was not worth to add another year for the limited luminosity, the limited statistics it would add. But so we use the 3 major years of run 2. So to collect data, let's say we can have a lot of collision, but to collect data we need also a very good online selection system, because we cannot save all the collisions, all the data from all the collisions that happen at too high rate for our computing system to save everything. So what we do is to using the trigger. So the idea is to reduce the rate while keeping a very high physics reach. So saving the data that we want. So we have a 2-level trigger. Level 1 trigger that is based on custom electronics, ASICs and FPGAs, and there's an output rate of 100 kHz. In our case, for our decay, this trigger uses information from only the muon chambers to select events with 2 muons. And then high-level triggers that is based on software, and recently also using hybrid computing, both CPUs and GPUs, and can read the full information of the detector and as an output rate of a few kilohertz. So the trigger used here you can have an overview, a picture of the events that these were collected in 2016 by different daemon triggers algorithms, and you can see them plotted as a function of the invariant mass. So you can see that we have generic triggers that scan the whole mass spectrum, and we have quite specific triggers that target specific signatures useful for B-physics analysis, but not only B-physics but also heavy flavor analysis. So we had also a specific trigger dedicated to B2S mu events that was requiring a pair of muons with PT at 4 GeV and an additional track at 1.2 GeV. And it was applying, in order to keep the rate under control, it was applying the selection on the, it was producing a common vertex between the three objects and applying the quality criteria and displacement from the interaction region. So you can see here the rate, the amount of events collected by this trigger is the low mass W plus tracker, the one here. And indeed, this particular muon, we don't want a narrow daemon invariant mass region, because as said, we need to analyze the full Q-square spectrum. So the Q-square spectrum of this trigger was scanning from around 1 to around 5 GeV squares. So no, sorry, from 1 to 5 GeV. Okay. So how do we, now that we collect this data set, how do we reconstruct our candidate and select it? So to reconstruct the candidate, we put together two opposite sign muons and two opposite sign hadronic tracks in our event. So we pass from this situation to this situation, and we require that these two muons and one of the hadronic tracks are compatible with the one that triggered the events. So you can see that from a quite messy and indistinguishable situation, we managed to get to a single candidate, let's say, so with the two muons and the two tracks. So this is a real event that was collected in 2018 and is part of our analysis. So it's also interesting to see how these events look usually, instead of just the drawings that we can do to explain. One limitation that we have that impact B-physics also, in particular quite a bit, is that the CMS don't have particular ID capabilities for the hadronic tracks. So what we can see is two muons, a positive track and a negative track. So we cannot say which is the kaon and which is the python. So we need to guess, and the best guess we can make is by combining the two possible invariant masses of the two hadronic tracks and choose the one that is closer to the mass of the PDG of the key star. So this produces a result that has a mistake rate of only 13%, that is quite good, and we will show that even with this kind of events, the mistake events, so where we assign the wrong masses to the two tracks, we are still able to extract physical information from this to the fit. So it's not all bad. And once we build the candidate for particles and we assign the masses, we can then apply a BDT selection that use again decay vertex quality and displacement for the as inputs, along with isolation and the mass of the K-pi system used again here. To perform selection, to reject as much as possible the backgrounds. So this is trained using I build like signal from Monte Carlo simulation of our signal, and the background we don't want to make assumption using Monte Carlo of the background sources entering in our decay, so we use the data sidebands to describe our background. So, what are the sources of background that we expect and we want to reject? We have the major source is the combinatorial background. So these are particles that come from independent processes and are grouped together to form a single candidate. And being then independent, the invariant mass of this, if we look at the invariant mass of the candidate, so put together the invariant mass of our 4 tracks, this has a smooth shape. So this is the main target of the BT, so the main background that it addresses, and the residual contamination. You can see this is an example of the final fit. So it's a bit of a spoiler, but yeah, it's useful to understand also the ratio between how much signal compared to how much background we have in our data set. And so this residual contamination can then be modeled using the sideband region. Since it's a smooth behavior, we can predict how it will look also under the signal peak. Other kind of backgrounds that are more nasty because they have peaking behavior, so they either only contribute under the signal peak, so we cannot use the sidebands to control them, to model them, or they only contribute in the sidebands, so they have the opposite problem. When we try to describe the combinatorial background, we are let's say, these peaking backgrounds would affect our modeling, and then under the signal peak, we would have a wrong assumption of how the background is looking like. So we want to reject them with dedicated cuts. So you can see here that what we have here is mostly similar decays, but with different flavor for the B and the kaon mesons. So we have the B plus to K plus mu, plus this is a single track, but then with an additional combinatorial track. And to reject this, we have vetoes on the possible three object system in our candidate around the mass of the B plus. Then for the B sub S to phi mu, where the phi decay to kaons, we apply veto on the two-track system in our candidate, assuming that both of them have the kaon mass, and so we cut around the phi mass. Then we have some this particular background where B plus decay producing a psi to S and a psi to S decay in a J psi and pion. So it's a cascade decay when one of the pions is lost. So this is mostly polluting the left sideband, and this can be selected rejecting applying some selection cuts on the masses of the partial systems in order to identify this decay. And finally, we also have a B sub S to KK mu muon that is similar to this one, but the two kaons are not resonant. That has a smaller branch ratio, but is still quite impactful, and we cannot apply a dedicated cut on the two kaons because they are not resonant. But this we see that is polluting both. It's quite flat as a function of the mass of the system, so it's polluting both the sideband regions and the signal regions, and it's quite limited. This is a percentage, it's only 4% of our signal, so it's just treated as combinatorial background in our analysis. We do this assumption. And then we also check that we don't have contamination from the B sub S to K star. This is the CKM suppressed B sub S to K star mu decay, and we see no evidence also of the lambda B decay. Okay, so once we remove all these decays, the other, let's say, major contamination that we have come from our resonant channels that, as I mentioned, we can build some dedicated regions in our Q-square spectrum to contain them. So this is the first thing we do, and use them as control channels. However, there are some effects that cause them also to leak in the Q-square regions where we have our signal. So the first one is some biases in the reconstruction of the momenta of the muons that cause a shift in the Q-square. The most common thing is when one of the muons irradiates a photon, and so we don't reconstruct the photon, it's a soft photon, but it shifts its momentum and to our lower values. And so you can see here in these 2D plots, this is with our data set. The yellow bands are the regions that we define to contain the resonant contamination, but you can see also this diagonal behavior. So this is on the x-axis we have the Q-square, and on the y-axis we have the invariant mass of the candidate. And basically, when this happens, when there is a bias in the reconstruction of one of the muons, what we can do is to indeed use the fact that both the Q-square and the invariant mass are shifted and apply a diagonal cut. So we are able to reject this tail of the resonant channel that let's say will contaminate only the lower sideband using this diagonal cut, and we lose a bit of events of background in our sideband, but this is acceptable in order to reduce this background. Another source of leakage, let's say another effect that caused these resonant channels to leak in our signal channel are cases where one muon and one hadron have a swap identification. So we have a B0 to J psi K star event where one muon from the J psi and one hadron from the K star have identification swapped. Usually this happens when they're very close and the muon chamber information from the muon are assigned wrongly to the hadron one. And this causes when we compute then the two muon invariant mass, we are not using the actual two muons that would resonate at the J psi value or psi2s value, but we are using one muon and one track that then has different Q-square values. This is a very rare effect, 10 to the minus 4 to 10 to the minus 5, but since our resonant channel is 3 orders of magnitude more intense than our signal, even a contamination like this would induce an order of up to 10% contamination in our signal, and these events have very distinctive features in the angular distributions, so we saw them very clearly in our distribution, so we had to reject them. And so we apply some cuts on this, swapping back testing to swap back the identification of the muons and the hadrons, and basically then cutting on the invariant masses with the hypothesis. Okay, so now that I explained how we build the dataset, let's see how we then perform the analysis, how we fit them. So we use an ambient maximum likelihood fit to our four-dimensional distribution. So the three angles that I mentioned earlier and the candidate invariant mass. As I mentioned earlier, this analysis is performed in bin of Q-square. So in each bin, we don't use the dependence on Q-square, but we just basically measure an average value of the angular parameters in this Q-square range. This is the model that we use to describe it. So we have a component for the signal with the correct k-pi assignment, a component for the signal with the wrong k-pi assignment that indeed, as I mentioned earlier, since these are signal events, we can still extract physical information from them, just adjusting all the dependence on angles accordingly, of course. And these two are linked with these ratio parameters that controls the ratio between the two in our dataset, and then a component for the background. Okay, so each of these components is composed by a signal mass shape. So basically, this is the shape of our signal, and that is estimated using simulation and then refined on data to account for differences between simulation and data. We have an angular decay rate that is the one I presented at in the previous section. So it's the dependence on the P parameters NFL. Then we have some functions that are used to describe the efficiency. This is quite important. So since all our selections have a strong impact on the angular shape of our signal, it's very important to control what is this effect, and what we want to do then is to then include in the fit model this shape. So multiplying our expected shape by this efficiency should then return a model that is consistent with what the angular shape that we would observe in the data. And this is done, as you can see, independently for correct tag and mistag events, and this is estimated on simulation. Also, the background model is split between mass shape that is fully data-driven and the background shape that is also estimated on data using the sidebands. So, I mentioned that we use 3 years of data taking, and what we do is to do a simultaneous fit over the 3 datasets, keeping the common angular parameter. We don't expect the angular decay rate to change from year to year because it contains the physical observable dependence. But all the other components, so masses and efficiencies, are independently estimated for each year to account for differences in the detector, in the triggers, and so on, since our detector changed quite a bit along the data taking run. So, the efficiency, so as I mentioned, it's very important to have a good estimation of how our selections affect the efficiency, and indeed you see here, these are the projection of the efficiency function along the three angular variables, and you can see that it's far to be a flat efficiency. There are some sculpting of the distribution, angular distributions. So what we want is to have an efficiency model that is fully three-dimensional and so describe the full angular dependence of this efficiency. So this is done with simulation and separately for correctly and wrong tag. And in order to both being able to describe narrow features like the one at the borders of the costa K and costa L parameters, variables, sorry, and also being robust for the low in regions where there is a low statistics of events. So this is a fully three-dimensional function. So even if we have Monte Carlo samples that are generated with a lot of events, we still have in some regions like we are working after applying all the selection of the analysis selection with the quite sparsely populated events, especially for the mistag category. So we need something that is both robust but also precise when describing the features, and so we use these non-parametric kernel density estimators to describe the numerator of our efficiency, the denominator of our efficiency, and then we take the ratio of the two functions. Since this is fully based on simulation, we need to make sure that our simulation is reliably describing the data, so we are not affected by differences between the two. So what we do is to use the GPSI resonance channel to compare the kinematic distribution that we have signal in data and signal in simulation, and apply correction, so apply reweighting of our Monte Carlo model. And so this efficiency accounts for this reweighting. So to describe the background, also this is a quite challenging procedure of our analysis, because well, we are using the sidebands. I showed you earlier an example of one being, you can see that in the sidebands, here we are talking about a region between 5 and 5.1 and above 5.45. So we have quite some events. So you can see that let's say, we can maybe reach a few hundreds, 1,000 maybe. But the problem is that we want a full three-dimensional parameterization of the background in order to fully describe the correlation between the angles also in the background. And when we have 1,000 events, when you split them in this three-dimensional phase space, they also here the statistics is really a problem. So we found the best procedure is to use a model based on three-dimensional Bernstein polynomial that controlling the coefficient of Bernstein polynomial allow us to ensure that the result is positively defined. And also we then tune the degree of the polynomials in order to have a good accuracy of the shapes, so asking a quality on the p-value, but also a stability in this fit to determine the coefficients. So, so this is how we managed to extract this distribution, these shapes. Finally, to conclude, as I mentioned, the signal mass model is evaluated on simulation and is using a combination of Gaussian function and crystal ball function that are Gaussians but using higher tails, so allowing also for asymmetric shapes of the signal, as you can notice already from this signal shape here. So basically how we do, we estimate the parameters of these Gaussians and crystal balls on simulations, and then we let them float in the data, but using constraints from these results of the simulation. So we don't manage to completely have a data-driven approach to describe the signal in data because these shapes are quite complex, but we managed to find in this way a compromise between fully relying Monte Carlo and just being data-driven. The background is simply a falling exponential, so it's also, this is fully data-driven, and you can see that it's quite easily, quite nicely describing the background in the sidebands. So one very important part of the analysis in our experiments is the evaluation of the systematic uncertainties. Here there is the list of this full set of systematics. I won't go through all of them. Just let me divide them in three categories. The one that are dependent on the statistics that we have in our dataset in Monte Carlo, especially when producing the model for the background or producing the efficiency, the model for our efficiency. So limited statistics here propagate to an uncertainty on the results, of course. So this is accounted with these systematics. There are some systematic due to some possible bias given the assumption or choices that we make in our models. So when we choose how to model a distribution, we could introduce these biases, and so we try usually different models, different shapes, and we build systematics for this. And finally, some biases that are introduced by the actually performing a fit procedure with realistic conditions. So, so this is basically performed by comparing fit on a simulation with high statistics, so a lot of data, and fit with subsamples, so producing these pools, the pool of the results. It's or accounting for differences between simulation and data, for example, for the efficiency, as I mentioned earlier. So everything is included in this kind of this class of systematics. In any case, here you can see the size of the systematics uncertainty, the color bars here. This is for different bins of the Q-square regions. And this is for the P5 prime parameter. So there are, just use it as an example. And you can compare them with the statistical uncertainty that is the full white box. And you can see that even, let's say, it's important to have this full analysis of systematics, but then this measurement is still statistically dominated. So this is an example of the results in one of the Q-square bins. result of the fit. You can see the 4 projections on the three angular variables and the invariant mass. And you can see the background model, the signal model in red, and then the total model in blue. And these are the results of the analysis. So here we have basically for only 3 parameters, the other are in the backup. But for 3 parameters, we plot the results of these parameters in the bins of Q square. The grayed areas are the resonant regions, the virtual resonant regions. And we compare them with 4 different models for the standard model predictions. Just to mention a few things about these models, starting from the EOS. This is using the most updated calculation of local and non-local form factors, included to produce this prediction on the angular parameters. Yeah, so it is. But also the ABCDMN prediction use the same ingredients as EOS, but combine them using some more conservative assumptions on whether they can be in a constructive or destructive interference between them. There are some more conservative consideration in the ABCDMN prediction. Then we have the Flavio predictions that are using for the non-local factor some QCD factorization approach that is a bit outdated approach, but it's still interesting to see the comparison with the other predictions. And finally, the F-fit that I believe here is not visible for some reason. It's not done on purpose, I promise. In the PDF version is there, but probably the projector is not showing them. But these, well, you will have to trust me that have quite big uncertainties and central values shifted toward our measurement. So out of all the other predictions, the F-fit ones are the one more. The only one consistent across the Q square and all the parameters, consistent with our measurement. Because why do they have, let's say, what distinguishes them is they use very conservative approaches when deciding how to compute non-local form factors and their uncertainties. So, yeah, so basically, this group, let's say the group producing these predictions has always been quite skeptical about how certain, how robust are the non-local form factor estimation, especially because of the charm loop, the impact of the charm loop in the non-local form factors. So they always use this larger, let's say, more let's say conservative approach to do this, but this results in like huge error bars that basically are not really predicting anything because they cover half of the allowed range of the parameters. So yeah. Okay, but okay, then this is the overview of the predictions. So what we can see is that for P2 and P5 prime, I chose them on purpose because they present some tensions in the low Q square area, especially just below the gypsy resonance. And you can see, yeah, that this presentation with especially with the EOS, that is the more aggressive for what concerns the form factors choice used, but also, especially in mean-tree, also for the ABCDMN. Final note is that some regions of Q square don't have prediction computed there because there are no reliable estimation of the form factors in those regions. It's still interesting to do the analysis because of future proofing is still important. Like if in the future we will have the possibility of having estimations also in these areas, we can hide them. But still, here there is no comparison available. What about comparing with the previous results, previous measurement? Here you can see that there is still the same two parameters, P2 and P5 prime. The others are again in the cup, if you're interested, but the others also are at the same results. That there is a generally very good agreement with the LCD measurement. You can see that previous measurement have quite large uncertainties, so it's difficult. Like there is agreement because, but let's say it's difficult to say anything. But I believe adding this measurement to the current LCD one is really creating a quite solid experimental picture from this. So this is quite important confirmation of what's already there. Like a real quantitative comparison with LCD is not really possible because the choice of the Q-square bins is slightly different. So you can see from comparing the horizontal bars. But you can see that precision are comparable and the central value is quite in good agreement. I don't know how much time I have. See, like okay, very quicker. So three words only for each slide of this. And sorry for taking too long. For run 3, we have a very good trigger in place that we increase the rate allocated to this analysis. We increase the mass window and lower the requirements. So very promising to extend this analysis for run 3. You can see here the spectrum collected. Projection for high luminosity. We have some available based on run 1 results that show also how we can split the Q-square bin in a finer bin. Now, currently we're working on new projection based on run 2 for submission to the European strategy. They are not public yet, so I cannot show them yet, but we're working on them. There is a very interesting alternative approach that I won't mention, but LHC tried this ambient analysis where they directly computed the Wilson coefficient and non-local for factors directly from experiments. Result is that the resultant C9, so the most interesting parameter, is that is still compatible with the previous results, but now the uncertainty is quite larger, so the tension is gone down compared to the previous result. And just a quick question to conclude. Let's say, is it still interesting? I think this set of prediction that some of them are compatible, some of them are not. Is it still interesting to continue doing this analysis with higher precision, with larger data set, or should we just wait for them to understand better these non-local for factors and let's say, I think the answer is yes, because it's interesting, because more precise measurement and performed in finer bins of the Q-square can really help also, so we can help from the experimental point of view to disentangle the origin of this tension. Because the impact from non-local for factors have dependence on Q-square and on the decay mode. You can see here an example of the results before in 2023, so without this analysis included. But you can see different colors are different, the impact of different decay modes and in different ranges of Q-square. So an impact from non-local for factors on this C9 would be Q-square dependent, while impact from beyond the standard model physics is universal. So having a better picture here, lower uncertainties and finer binning, surely will help understanding and disentangling this. So looking forward for performing this analysis in the future business.
Thank you very much, Alessio.